context of a planar symmetry. So here we have got an infinite plane of charge. Why do we take infinite lines or planes of charge? Only then the situation is perfectly symmetric. So here we have got an infinite plane of charge, and that has this positive charge on its surface. Now we draw a Gaussian surface, which is a cylinder, as shown over here. Because of the symmetry of the situation, electric field lines can only and only be perpendicular to the given plane. The moment the electric field has any component that is along the plane in any direction, then in that case we will say that why is this direction preferential, or why is this direction preferred over any other direction, like this. So any direction along the plane is equivalent, and hence electric field cannot be along that direction. The only symmetric direction allowed is the perpendicular direction, and hence the electric field lines are going to be in a direction perpendicular to the plane surface, and towards the left also the electric field moves like so. So hereby, if we look at this particular Gaussian surface, then in that case, in this particular scenario, for the curved surface area, the electric flux is going to be 0, because the electric field lines are parallel to the curved surface. They are perpendicular to the plane, and hence they are parallel to the curved surface, because this particular Gaussian surface itself is perpendicular to the plane. The charge enclosed by this Gaussian surface is represented over here, and we know that sigma happens to be the surface charge density. So the charge enclosed is going to be equal to sigma times area. Why? Because sigma is equal to q divided by area. So charge enclosed will be equal to sigma times area, where this is the area that we are talking about. Now, in order to apply Gauss law, we would like to find out how much flux emanates from the surface, and we have just seen that the flux is going to emanate only from the planar surfaces. So let us say this cylinder is symmetrically located, then in that case the flux that is emanating from the planar surfaces can be written down as EA towards the right hand side plus EA towards the left hand side. This is the net flux that emanates from this particular Gaussian surface. That is equal to 2 times EA, and this happens to be equal to Q enclosed divided by epsilon naught. Q enclosed we know is sigma times A, sigma being the planar charge density. Therefore, we can write down 2 times EA is equal to sigma times A divided by epsilon naught. We cancel out the areas, and hence we get the electric field to be equal to sigma upon 2 epsilon naught. And this is the answer for the electric field for a uniformly charged infinite plane sheet. Now let us look at a sheet that is plane but made up of conducting material and grounded towards the left hand side. So here electric field will be equal to 0. Electric field is not present, so electric field will be equal to 0 towards the left hand side. So the only electric field that is present is towards the right hand side. This is a conducting sheet that is charged and grounded on the left hand side. So all the charge that is present only on the right hand side, and none is present on the left hand side, and hence electric field also will be present on the right hand side only. Here if we apply Gauss's law and try to find out the net flux, we get phi E is equal to EA rather than 2EA, and this will be equal to Q enclosed upon epsilon naught. Q enclosed remains the same. Q enclosed is nothing but sigma times A. So this is equal to sigma A divided by epsilon naught. That happens to be equal to EA. After we cancel the area, we get E to be equal to sigma upon epsilon naught. So this is the answer, wherein on one side there is no electric field. then the answer comes out to be E is equal to sigma upon epsilon naught. This typically happens in case of conducting planes that are grounded on one side and hence all the electric charge is present on the other side only. We can remember this answer to be the answer in cases where electric field is present only in one side of the plane. Charge and E if the electric field is present on both the sides of the plane, then we'll get sigma upon 2 epsilon naught as the magnitude of the electric field. Please note that this electric field is uniform throughout space and does not depend upon the distance from the plane. So it is uniform all throughout space. That means even if we are further away from this infinite plane, we'll have the same magnitude of the electric field compared to if we are closer to the infinite plane. Similarly, over here as well, the electric field is uniform towards the right hand side and towards the left hand side the electric field is 0. And thus, we have studied the application of Gauss's law for the cases of planar symmetry.